All right, we're going to get started.
All right, I'm happy to introduce a new speaker now. Ian Moult is going to be giving 3 lectures on CFTs and colliders, some mixture. He's visiting from Yale, so yeah, welcome Ian. Thank you.
Perfect. Yeah, so hopefully you're all having fun at the school. I came as a student, it was a lot of fun, and it's very fun to be back as a lecturer. So the title I was given was Conformal Field Theories for Particle Physics. It's on, maybe I can move it closer. Okay. Okay, can you hear me, or?
I can hear you fine, just making sure.
Okay. Conformal field theories for particle physics. And so I actually don't think this is a very good title for what I'm going to be talking about. And so in particular, so what this lecture series will not be is a kind of overview of Euclidean CFTs. So this is something that exists in many textbooks. And so one can go and kind of read about this if this is what one wants to learn. So instead, what I'm going to be trying to talk about is how one can phrase certain questions that are of interest in collider physics in a language where you can use techniques from more formal field theory, and in particular from conformal field theory, which is just a specific example of conformal field theories. And so maybe a kind of better title for these lectures will just be Field Theory for Collider Physics. And then conformal field theories are just a specific instance of this. And so my hope is that this will kind of complement nicely the lectures by Ben Nachman and Stefan, but it will give a kind of very different perspective, which hopefully you'll see how they kind of interplay together. And so my hope is that people will ask many questions throughout to make it more fun. So I wanted, because this will be a little bit different than most of the talks that have been so far in the school, I wanted to kind of very clearly spell out at least my personal motivation for why this is interesting. And so the real motivation is if you look at all these very complicated event displays, for example, in Ben's talk last night, the problem as a theorist, if you want to understand these in detail, is that the real world is very hard. And in particular, depending on your taste, it may be too hard. So what we want to do in these cases, or one thing which is nice often as a theorist, is to try and retreat to certain toy models or toy theories where you have better analytic control. And so the reason you like to do this is it would be very nice to have, for example, some toy theory where you can exactly solve, for example, what happens at a collider and really kind of understand and get some intuition for it and then apply it more broadly. And so, of course, in like non-relativistic quantum mechanics, this is what you do. You study the hydrogen atom, you kind of learn or you gain some intuition, and then you apply it to more general setups. And so what we'd like is to have some kind of toy collider where you can really understand, for example, like are there jets, and how to ask nice questions about it, and then apply this intuition, ideally go back towards the real world and actually learn something about real world collider physics. And so one of the problems that you encounter if you try and take this approach, so this is also done, for example, in many other areas, so for example, in scattering amplitudes or just quantum field theory in general, is you go over to a set of toy theories and you know kind of what questions to ask. And so one of the problems that you run into when you try and do this for collider physics, so you can go ask your kind of formal friend, for example, for what their favorite toy theories are. And so I'll just write some down. And again, it doesn't matter if people aren't familiar with these. I just want to kind of show, or words people have probably seen before. And so depending on who you talk to, they might say different things. They might say, for example, they like studying the Ising conformal field theory. And they do this using, for example, the conformal bootstrap. You might talk to some other friend who studies, for example, n equals 4 superconducting mills, or some variant of it, which are also conformal field theories. and you might be using some fancier techniques, let's say like integrability. Or you might talk to some other friend who studies, for example, holographic conformal field theories using the idea of CFT correspondence. And so one thing you'll notice in all these examples have in common is that they're all kind of examples of conformal field theories. So most of these toy theories that people study in the formal field theory world are conformal field theories.
Ian, as you write low, could you lift the board?
Yeah, sure. Okay. And so now the problem is, so you might say, oh, that's kind of great. So can I try and understand? So let's say I exactly solve one of these theories. Can you ask in these theories questions relevant for collider physics? So let's say I lived in the 3D icing model. Would I be able to exactly understand collider physics in this world? And so one of the problems is that then the formal person may ask kind of what types of questions do you typically ask in collider physics? And so there was a nice talk yesterday by Ben, and so he wrote something which I'll purposely pick on a little bit to illustrate this point. So he said that what you do is you take, for example, the Lagrangian which describes nature, you feed it into some collider, and then out you get a bunch of particles. And you can cluster them, for example, into like jets or do machine learning or all these whatever you want on them. And so one thing you might say is, okay, I just repeat the same process with my favorite field theory over here. So I can just send in my kind of toy theory. I do some kind of collider experiment in this. And then, so the problem is generically in these theories, in particular these toy theories, is you do not get out particles because they're all conformal field theories. And so you're then just kind of stuck at how you talk about questions in collider physics in a way where you can actually make some progress. So you have all these very nice toy models where you can do all these nice things, and the kind of questions which people are asking in collider physics are just very difficult or impossible or ill-posed in these models. And so this was actually the original motivation of, in particular, Maldacena and Hoffman. Because if you want to ask, for example, questions of relevance for collider physics in holographic CFTs, you first have to start by just asking a completely different set of questions. Yeah. Good. So that's a very good question. We'll get to that in a second. Oh, yeah, sorry. So the question is, of course, so in, let's say, like LHC, you collide particles. So if you don't have particles, you can't necessarily collide them. But you can do, generically in these theories, you'll often have operators. Or in just a normal conformal field theory, you have local operators. And so you can do the analog of like an E plus E minus LEP collider. And this is literally what you do in some like condensed matter experiment. So you'd have like a table where you prepare your thing, and then I can just hit it with some local operator like in the middle. So I just ping it. And so that's like dropping like an operator at some particular location. And so this is the exact analog of like LEP. So there, the initial states, which are like E plus E minus, are not charged under QCD. And so from that perspective, it's really like pinging, like LEP is literally like pinging the QCD vacuum with like this particular current. And so this is something you can do both in real world experiments, but also just in a toy or a condensed matter experiment, you can just ping it with some local operator. And so you have to slightly, it's not exactly a collider, but it's still just kind of like exciting some system. And then you could look what goes out to infinity. So you could just hit this with different things and then measure things at infinity. And so this will be exactly part of the types of questions of what one wants to rephrase is to have kind of sharp versions of what a collider is in these different theories. Yeah, so that's a very good question. Yeah. Any other questions before we keep going? Okay. So at this point, there's kind of two ways to proceed. So the first is you can just say these toy models or toy theories are too simple for the types of questions that we want to ask. And so I think this is a bad answer because in particular, if they're so simple, then you should be able to answer all the questions you want about them. And so the second one is that questions in collider physics should be rephrased in a language which makes more contact with questions you can ask in these kind of toy or nice theories. And so, of course, I think the real answer to this lies somewhere in the middle of this. But for these talks, what I'm going to push is this particular direction to try and ask kind of very simple questions where we can get nice answers in toy theories and then kind of move back towards the real world. OK. So the first thing that I want to do is just to kind of highlight a little bit the difference in language between these toy theories and what you often ask in collider physics. And then this will kind of build up a dictionary of what we want to kind of equate that we'll go through in the rest of the lectures. So on one side, we can kind of have conformal field theories, or just, it doesn't really matter if they're conformal or not, just field theories. And then on the other side, we can have colliders. And so the first thing we want to, or which we'll make more precise, is what types of questions or what observables do you ask in the two? And so if you have, so these are often used, for example, for tabletop experiments, or if you pick up a kind of book like in Peskin and Schroeder, or some book on conformal field theory, what you typically measure are correlation functions of local operators. So you have some operators at different locations. And you measure some correlation functions. On the other hand, in collider physics, what you often measure are, let's say, cross-sections or certain kind of jet observables, which have been mentioned in Ben's talk and will be mentioned in more, definitely more detail in Stefan's talk. So then once you have your observables in both cases, you have kind of calculational techniques of how you analyze them. So in the case of conformal field theories, you have, and again, so I'll explain these things later on. These are just words that hopefully you've seen and will make precise throughout. So here, what you do is you typically can't, you just don't brute force compute this. You have approaches for kind of breaking them into simpler pieces. So the way that you proceed is to kind of break them into simpler pieces. And this goes under the name of operator product expansions. Conformal blocks, etc. On this side, so if you're computing some complicated jet cross-section at the LHC, again, it's rare that you compute it at just completely exactly. And so this is, for example, also what the parton shower that Stefan will talk about. And so the way that you address this is instead of with this operator product expansion, you typically address this using what are referred to as factorization theorems. Which again kind of break these up into certain building blocks. So for example, you might factorize into some hard piece, and then some, for example, jet piece, which describes the jet dynamics. And then in both cases, after you do this kind of decomposition into simpler pieces, you typically study the pieces which contribute. So you organize the operators that contribute. And so in the conformal field theory case, you typically organize these by operator dimensions. So hopefully you can read this. And spin. Whereas and you have certain kind of scaling relations depending on the particular dimensions and spins of the operators that contribute. On the other hand, on this side, what you typically have are renormalization group equations. Which describe the scaling behavior, again, of the specific pieces which enter your factorized description. And so these things have names, so which you may have heard about, for example. So these will appear in Stefan's lecture, for example, splitting functions, or DGLAP evolution. And so if you look at these naively look quite different, and in particular the language is extremely different. But the actual approach for doing this is very, very similar. And so in particular, what I want to do in the rest of the lectures is to kind of show how if you ask a specific type of questions here, then these are essentially exactly the same thing. And so you'll be able to rephrase certain questions in collider physics in terms of very precise correlation functions. And then you can use very similar techniques where there's kind of a manifest correspondence between these kind of factorization theorems that one typically uses over here, or for example, these DGLAP evolution equations for the splitting functions, where these just map to very clear questions on the conformal field theory side. And so it will allow one to find kind of analogs of all the things that one likes in conformal field theory world, all the things one likes in collider physics world in terms of things in conformal field theory world. And then the nice thing about this is we'll then be able to extract them and kind of use the powerful machinery in these theories to kind of understand them very nicely, at least in these worlds. And then by doing that, hopefully learn something back. Sure.
Given to operators, is the OP spectrum universal or theory dependent?
It's definitely theory dependent, yeah. Good. So one is asking, if I have some operators, how does this depend, for example, on the dynamics of the theory? And so in particular, that will be encoded in some sense in the scaling dimension. So it can be encoded both in the OPE coefficients, as we'll get to, but also just in the actual spectrum of the dimensions of the theory. And so we'll see, for example, when you do this, that we'll have certain exponents coming from the DGLAP evolution equation, and these will be, you'll have a similar scaling law in any theory, but the actual dynamics of the theory will be encoded in the value of that anomalous dimension. And so this is why one of the things which is nice about this language is we'll be able to see kind of what properties are universal, and then they'll just take on a different value in different field theories. So we'll be able to make kind of generic statements about, let's say, jet physics depending on just a particular anomalous dimension in a particular field theory. And then the value of that anomalous dimension, you just have to either compute or go look up or get for somewhere for the specific field theory that you happen to want to understand. And so it allows a kind of more universal picture of some of these questions. Yes? Yes, but so the types of questions that we'll be analyzing are very different. And so in particular, so those are primarily space-like questions. And so this is what I'll be getting to in the second half, is a kind of new set of tools which are much more recent, which allow one to analyze what are referred to as time-like questions. And so these really use a new set of, for example, operator product expansions. So this will not be, as I said over here, this will not be kind of the standard Euclidean OPE. And so what is needed is actually kind of new types of operator product expansions for more non-local operators. And so these are things which came out primarily in the kind of, so this was about, they were first introduced in about 2007 in these papers. So what it is trying to do is exactly as you say. So those questions for like DIS and E plus E minus are phrased very sharply in terms of the Euclidean OPE. And what one wants to have is a similarly precise language for a more set of Lorentzian type questions or jet type questions. So it's trying to kind of extend those tools, because there it's very nice that you have a beautiful correspondence, and to extend these to questions where you measure properties about, for example, the jets in the final state. And so it'll be, yes, if I was more precise, so for example, down here for DGLAP, there's both a time-like DGLAP and a space-like DGLAP. And the space-like DGLAP is what is related to standard local operators. And so the anomalous dimensions which appear in the time-like DGLAP are not related to standard local operators. And so these are things which have now been well understood on the conformal field theory side. And so it allows a kind of, and in particular, it's now understood precisely how to relate them. And so it's kind of extending that type of very precise and very sharp language to jet-type questions. But yeah, that's and that's kind of in some sense the goal of this type of work. Yeah.
Non-local, so if you're using two operators, it's the other operator that we're getting outside the radius of.
Good. So these questions are getting a bit beyond what we'll get to for a little bit. But one of the questions, or one of the things, is we'll be looking at in particular Lorentzian singularities. So this will not be when two operators approach each other to an actual small distance, but it will be when, for example, if I have two operators and I bring them close to a null line. So then the set of operators that appear are, so then as you just said, the standard OPE will not converge. And so what you have to do is to identify a new set of operators which describe the leading behavior in these limits. And so these will be non-local operators, and so these will be the things which are of relevance in collider physics contexts. And so we'll first try and set up the collider physics context in terms of these certain non-local operators in the field theory. And then one will be naturally led to study operator product expansions between these more complicated objects. Yes. Any other questions before going on? Because it's good to hopefully have the motivation. Okay. Good. And so again, just to summarize the motivation for why we want to kind of do this. So apart from intrinsic interest, the main kind of reasons that we want to do is to develop new computational tools which can be applied to ask questions about collider physics in real-world QCD, and then also to kind of sharpen the set of questions which we ask about collider physics. Good. And so the kind of plan of what I want to cover in these 3 lectures, and it will be a little bit dependent on how much time we have. So the first thing we want to understand is what are the relevant kind of observables that we want to talk about, and how do we express them in terms of operators. So what we first want to learn are the relevant observables for collider physics, plus what are referred to as detector operators. And so this will get one into the world of these non-local operators who we need to study the behavior of. So this will then motivate us, once we've set this up, it will allow us to rephrase certain questions about collider physics observables in terms of correlation functions. And so we'll then study how we can obtain collider physics from correlation functions. And so this will be nice because then what it means is if someone is able to, for example, get some specific correlation function, you can use it to make some nice prediction that you might care about from a collider physics perspective. And then the third day, or the third topic, will be to study the operator product expansion structure for these operators and its relation to factorization, scaling, and renormalization group equations. And so we'll kind of we'll start from things which are intentionally extremely simple so that we understand them very precisely, and then move towards answering. So the original questions we will answer will not be very interesting, and then we'll slowly build them up towards questions which are actually of relevance, for example, for interesting measurements like collider physics experiments. But so are there any questions on this general motivation before we continue? No. Okay. Okay, so the first thing we want to understand is what types of questions we want to ask. So what we want to study are observables, in particular collider physics observables, and detector operators. And so in particular, the goal of this section will be to introduce certain observables which are extremely clean theoretically, and exist in generic quantum field theories. And so I just want to build these up slowly by kind of emphasizing why one is interested in this specific regime. So first, I want to kind of build up other examples of nice observables. Because these depend very much on the particular theory you're interested in and the particular class of experiments. So a very nice class of observables are exclusive cross-sections. So these are something, for example, which you study in Peskin and Schroeder. And so, for example, if you have some theory with massive particles, so then you can nicely scatter those particles. For example, in real-world QCD, you have pions, and you can scatter them in, for example, a fully exclusive, let's say 2 to 2 scattering amplitude. And so typically you consider this if you're at energies kind of around or of order the kind of mass of these particles. So you can study them, and you can scatter them, and you can describe them, for example, with the chiral Lagrangian. And so this is something which has a very nice set of properties. So you understand very nicely, for example, their analytic structure. You have nice ways of computing them, and they're very nice theoretical objects. The second class of nice theoretical objects, which is also what appears, for example, in Peskin and Schroeder, are correlation functions. So the second example are just correlation functions of local operators. Which again I drew like before. And so these are nice if I have, for example, some tabletop experiment, but they're not as useful for collider physics because you can't move them off to infinity, which is what you typically want to do in a collider. And so again, these are very nice, which is why they're again included in standard textbooks. So you also understand their very nice analytic structure. You have nice ways of computing them, et cetera, et cetera. And so they're very well controlled objects. But now what you can do is to kind of consider some limit of what we're actually doing as you go to the LHC. So if we move to the LHC, or to some very high energy collider, And so I want to consider a case where you have the energy is way, way bigger than the typical mass of the particles in your theory. So this is, of course, the case, for example, the LHC. You have this at some TeV, and these are kind of pions that are coming out. And so now what you get out are these kind of sprays of, let's say, hundreds of pions which are coming out. And they're coming out to your detectors, which are off at asymptotic infinity. And so now the question that you want to ask is kind of what questions can you ask that have a similar nice analytic structure to these observables that you studied in the past. So what questions about this can we ask? And so here, so one thing which you can do, and which is kind of typically done experimentally, is sometimes it's useful to, for example, group them into specific cones of jets, so like this. But this is very difficult theoretically because you have to give some definition, for example, for how you group them. This involves kind of talking about particles. And also if you try and, for example, compute these will not be very nice objects. So they may be very practical, but they don't have a very nice theoretical structure. So there's kind of no analog of these very nice properties for this. And so what we'd like to understand is there kind of an equally nice class of observables which we can ask about in this limit of kind of very high multiplicity collisions. And so one way of kind of organizing one's thinking about this question is to take the limit where you have, or where you don't have any particles in your theory, and you can either think of this as some infinitely high multiplicity, or just some kind of conformal field theory of just some kind of blobs of energy going off to infinity. And so then in that case, the question of kind of what can you actually ask about this is even more pressing, because you can't kind of cluster things into particles. And if you have an S matrix, or if you have a conformal field theory, you don't have an S matrix. And so because these typical questions of local operators are not what you measure at a collider where you have things coming off to infinity, you kind of have to come up with a new set of questions which you can ask. And in particular, so this is why it's kind of nice to study this limit of what are referred to as conformal colliders. Because it kind of makes you rethink about which questions you might ask about in a collider physics context. And so this, whether or not these questions end up being practically useful is a separate question, but at least kind of makes you think about why you ask the specific questions you do. And so there's kind of two reasons for doing this. So one, which is related to phenomenology, is that you're literally, this is something that happens in the real world. And so you have very, very high multiplicity collisions. And so you might want to use a different class of observables that are motivated by these conformal collider observables to describe them. So even though it's not a conformal field theory, it's kind of in this regime of very high multiplicity. And so it may be useful to kind of switch to talking about in this language. And the other reason, which this of course depends on one's particular taste, is literal conformal colliders. So these are not what you have at the LHC, but you can very well make some condensed matter system, which is a conformal system, and you can kind of ping it. So this is something you can really do in a lab. And then you kind of ask, what questions can you actually ask about this theory, and how do you use, for example, the data you know about that theory to answer these questions? Good. So are there any questions about this general setup? Yeah.
If you have a given process collider, how do you identify which operators collision function to calculate?
That's a very good question. Yeah.
Could you repeat the question?
Yeah, good. Sorry, I was. So the question is, let's say I just have something at the LHC. How do I know what operator I'm actually probing? And so at the LHC, that's a very complicated question. And so this will come back to, and this is related to your question earlier. And so you just go back, or you retreat to being able to say that you specify some particular set of operators. And so in the toy world, we can always do that. And then more generally, what you would say is that whatever you end up like pinging your system with, so there's a nice picture, which I can't do as well in chalk, but you can ping like with a hammer. And you want to write that as some sum over some local operators in your theory. So whatever you're kind of pinging, you as a theorist need to kind of decompose it into a basis of operators which have some nice property in the theory. And so this is, at the LHC, this is what you actually have to do, and we'll maybe get there by the later lectures. But those are things which you, hopefully, that you understand your setup well enough that you can actually do that.
I have one more question. The O's that you choose, are they uniquely fixed, or there is some guesswork that needs to be done?
So these O's, so ideally if I had some system, they would be, I could expand them. I have some basis, as we'll say, you have some basis of operators, which you can write any, so at the LHC, they're not really local operators, which makes it a little bit more complicated. And you need like part-on distribution functions and stuff. But at the, in the case where it's really a local, or you're really probing with some local excitation, you can just write it as a linear sum over some basis of operators that you particularly like. Yeah. And in particular, it would be ones that you have characterized beforehand. But for a kind of toy world, we can just assume that we have one particular operator and just kind of ping with that and then see what comes out. That's a very good question. Yes? Good. So if you have actual conformal symmetry, so what you want for an S matrix is to be able to have kind of asymptotic states. But in a field theory, because you can kind of rescale, you never actually get to this regime. And so you can think of, at a very loose sense, it's kind of, a conformal field theory is kind of like, you can think of it as just some very strongly coupled mush, at least for this toy kind of setup. And so you don't typically have like particle states. And so instead what you do are kind of typically correlation functions, or you can think of it as really like, here I can drop into some water and watch some ripples come out. And I don't really have like quasi-particle states. Instead, I just have some, which I'll talk about in a second, how to characterize. You have kind of operators, and then you can discuss the spectrum of those operators. But you don't have well-defined asymptotic stable particle states. And this will be reflective in that if you compute an exclusive scattering process, it will just be, if you do it in perturbation theory, it's, for example, infrared divergent. Whereas if you have a mass gap, then it's just a well-defined object with asymptotic states that you can define. Yeah.
Something with an operator, what do you mean?
Good. So, good. So, I'll write down that in a second. But you can really think of just acting with some local operator of your choice on the vacuum.
Okay.
So I can have some operator that has some, for example, well-defined momentum q, and I just act with it on the vacuum. And so that will produce some set of multi-particle states in general. And you can really think of it literally like if I have some tail is like hitting with a hammer, because that's just a local excitation. But it's just acting with some operator on the vacuum. Yeah.
If it's some momentum Q, it's not really local. Or like it's
So good. So it'll be an integral over a specific local operator. So typically in collider physics, we tune. That's a good point, and I'll show when we write it down. So typically in collider physics, what we specify is the momentum. But these can be obtained by essentially Fourier transforming just a local operator. Yes. Any more questions? Good. And so just before we actually start into how to do things, I just wanted to emphasize once again, just very clearly, the kind of motivation for these types of questions, both from a phenomenology and a theory perspective. So on the theory side, what one would like to understand as a more abstract question is what are the space of observables that you can measure at infinity in a CFT or in a generic field theory. And the more kind of colloquial way of saying that is in some abstract conformal field theory, what possible detectors could you build? So we build the LHC, but what possible kind of detectors could you put in infinity, and what quantities can they measure? The second is how you can, or how these are related to the more standard kind of local operators that we're used to talking about in quantum field theory. And in particular, if we kind of define some detector or some observable infinity, how do we compute it using the kind of normal machinery that we have? And then the third is, which I'll give some examples of later on, is how can we use these? So let's say, so often what one does, if you have some, for example, S matrix, is you can use, for example, dispersion relations to place constraints on your theory to kind of check, for example, if it's consistent. If you no longer have an S matrix or, for example, local correlation functions, you can ask how can you kind of, for example, probe the consistency or constrain, let's say with a bootstrap, the types of theories. So how do you constrain that don't have, for example, an S matrix or local correlation functions of local operators. And so this will lead us to some kind of, which I'll hopefully get to, some set of thought experiments that you can perform with colliders, which allow you to place interesting constraints on, for example, OPE coefficients or central charges of your theory. So it's kind of, even if you're a pure formal theorist, studying these collider physics events is a kind of nice way of thinking about things. And then, as I said, from the phenomenological side, so the phenomenological side is, for example, in a collider, can we identify universal properties in very complicated collision, which we can compute to high accuracies? And then how do we do these calculations? And so hopefully I'll get to explaining all these points. OK, so now we actually want to start actually doing something and writing down kind of the operators that we'll be studying. OK. So the first thing that we want to be able to do is to write down some kind of operators in the quantum field theory which enable a kind of simplified version of what we're actually doing in a collider physics experiment. And so in the standard collider physics experiment, we have all this stuff going out. And then we have a bunch of detectors which are off at infinity. And so at the LHC, you have, for example, hundreds of millions of these pixels, which measure, for example, charge and energy information at all different angles. And so here we're going to be much less ambitious. And we're going to imagine that we have a collider that has exactly one detector pixel at one particular direction. And so we're going to try and understand. So this will be at some particular direction, for example, in the sky, characterized by some unit vector. And so we'll try and understand if we can, or we will try and set up and see if we can understand in a generic quantum field theory how we study this. So if our collider just ran, we had one cell which was just sitting there. And so all we produce is kind of one number coming out of the LHC. And so you could do it as a function of this vector, but it's just kind of averaged over all collisions. For example, the energy that's coming out through this particular angle. And so this is, in some sense, the simplest possible collider physics observable that you can hope to understand. And so if you can't understand this, then yeah, you're in trouble. So what we want to do is to write down an operator. So typically when you have a calorimeter, what it's measuring is energy. But we can also imagine a kind of generalized detector which measures the flux of any quantity that you want in your theory. So it could be like electromagnetic charge or something like that, going through in some particular direction n hat. Specified by some unit vector like this. So let's try and just write down some operator. We'll start with the energy flux, and then we'll move to other currents in the theory. And so this is actually something which is not that difficult to do, is you can kind of guess what you'd want to do. So the first operator we'll write down is what is called the Anik operator. So this one it's named after a condition, which we'll get to later, which is the average null energy condition. And so what we'll try and do, or we can write down an operator which is supposed to measure the energy going in some particular direction specified by this unit vector n. So obviously, what we want to write this down, so it will be in terms of the stress tensor of our theory. So this is what measures the kind of energy of our theory. So I'll just write this and then explain it. Okay, so what am I doing when I actually do a collider physics experiment? I can imagine putting a little stress tensor off here at some particular time and along some particular direction. And what I want to do is then move that detector or that operator off to infinity. And so then what I'm doing when I do, or I can imagine what I'm doing when I'm doing a collider physics experiment, is just having that operator sit there for all time. So I kind of integrate this object over all time and just pick up the total energy flux which goes through this object. And so you can check, the simplest thing you can check, for example, is that this object has the correct dimensions. So for example, what is the dimension of the stress tensor in like 4 dimensions?
Why does the stress tensor have one component?
Sorry?
Why does the stress tensor have one component?
So maybe this is, so it's the T0I component.
Oh.
Sorry, yeah, sorry, this is a bit squished. So I'm taking the T0I component and dotting into the particular Ni vector. So that's a good, sorry, yeah. So what is the mass dimensions of the stress tensor? Does anyone know? 4. In D equals 4, it's 4. And then you'll see that these and this have -3. And so it has units of energy, which is good. Sorry. And so a good thing which you can do on the homework, so I'll give this as a homework exercise. So the simplest way that you can check that this object is sensible, which is a very nice exercise to do, is to just look at this object in a free field theory. So I can just shoot some particle which goes into my detector, so I can have some free particle momentum eigenstate. So as an exercise, what you can do is to check that this actually measures the energy. On a free particle state, or in just in free field theory. So you can just take, for example, a free scalar theory. You just write out the field in terms of creation and annihilation operators. And then from that, you can work out the expression for the stress tensor in terms of creation and annihilation operators. And you can just simplify what this object is when you take this integral to infinity. And so if you do this, what you get is some nice expression. So I'll give the answer. But this is a simple exercise which is worth going through. So what you find for this case is that you can nicely write this in terms of the standard creation and annihilation operators, where you just pick up an energy weighting. It now has this AP dagger, or AP dagger AP, and then you get a delta function when the momentum is aligned with the particular unit vector Ni. And so this is very nice, because then what you can do is you can act with this on just free particle momentum eigenstates. And so if you act with this on some state x, which is just a bunch of free particle states, so these are just free particle momentum eigenstates. What you find is that you just get a sum over all the particles which are in your state, like this. Their energy like this. And so one way of thinking about this is essentially free particle momentum states going in different directions are eigenstates of this operator with an eigenvalue that's the energy times this delta function, whether or not you're going in the correct direction or not. This is a delta 2. So you can think of it as in the angle. So I'm just writing in this a little bit weird way, but you should really think of it as like angles on the celestial sphere. So you can, yeah, this is it's nicer to write in like delta 2 in the like, I can write in maybe a better like omega or like the angular vector. So you just want to think about it in angles. So it's really on the celestial sphere. Yes, good question.
Also, do you use this energy condition?
Sorry?
Do you use the energy condition, the anic, to split that?
So no. So this we have not. So we will use the anic later to say interesting things about the properties of this operator. For now, this is just a definition, and it's called the anic operator. And so later we'll see that. So what the anic means is that the expectation value of this in some particular state is non-negative. And we'll see later that this is kind of a trivial statement from the perspective of collider physics, but that it will give very interesting constraints on, for example, data in the field theory.
That condition comes from first principle.
This can be proven, elsewhere. So I will not, I can show after this, so there's multiple different proofs. So there's one using quantum information, and then one just using kind of causality and basic principles. So it can be proven from first principles in unitary Lorentz invariant four-dimensional theories. And so this, is proven independently, and then we can apply it. And so historically, it was actually kind of done the reverse way, that people wrote down this operator, and then you can say, obviously, this is positive. Because that's what I say, like, if I really believe this corresponds to what I'm measuring, and so this is what was done in the paper by Malacine and Hoffman, is you just kind of say, obviously, this thing better be positive, and then you can derive constraints from those. And then afterwards, it was independently proven by different techniques. And so we'll come back later to how we can use this to say interesting things about the theory. Probably next lecture, yeah. Sorry, yeah.
These operators are independent.
Yeah, so we're picking a detector frame, yeah. So these operators and I will not, so there's much more detailed, I can give also, there's many lectures about just these particular objects, and they're very interesting in general, and you can put them just in general on some null plane. And so I've chosen a particular frame where I put them at infinity, and that will, because that's what is relevant for collider physics in particular, But in a conformal field theory, I can just switch between those different frames. And so that's something which is very nice for studying specific properties of these operators. In a non-conformal field theory, they become an actual, there's a difference between these different frames. And for that, it will matter, and in particular, this comes back to some of these questions about like space-like versus time-like. And so what you compute will matter in a generic theory which frame you pick. And so for colliders, they're kind of naturally at infinity, but they're equally interesting objects on any other null sheet or along just generic null rays. Yeah. Yes.
So is this observable infrared safe? I'm especially worried about collinear particles because we have this delta function. So if you can just fall outside of the picture, right, that changes your prediction.
Excellent. So we'll get to that in like 30 seconds. Yeah, but that's a very good question. So before getting to that, I just want to give another one which is not infrared safe, and then we'll go through why they're not. But it will end up being infrared safe. Yes. Good. Any more questions? Yes.
What is that average over? I can't see the subscript.
What is the average over? Yeah. This is just meaning if you take its expectation value in any state. So this is just some like state psi. So this could be the state produced by your local operator, but more generally in kind of just any, it's just the expectation value in the sense of like in a quantum mechanical state, the expectation value of the operator, yeah. And sorry, this was kind of a side comment that we'll get to this next lecture, and we'll discuss this in some detail. And so this is just a side comment related to this condition. Perfect, okay. And so this can, of course, be generalized. So this is for the particular case of the stress tensor. But you can do this, of course, for other charges or other operators. And so another one, which you might be tempted to do, is for electromagnetic or some U1 charge. So you can do the exact same thing. And in particular, it looks absolutely identical. Sorry, so this is a bit small. But I can do this for some current, Ji. And so again, you can check that this gives, for example, for like a U1 charge, the correct dimensions, right? So this charge has dimension 3, and so this is dimensionless, and so which, as you would expect, for the unit charge. So the more abstract goal, which we will not investigate too much, but it will relate to your question about infrared safety, which we'll get to in a second, is what you'd like to know is kind of given a theory, what are the well-defined detectors? And so in particular, I can easily write some of these objects down, but they might not be well defined. And so in particular, one of the questions you have to worry about is infrared and collinear safety. And so I will, since you asked the question, I will skip to that now. Okay, so one property that you might want of the detectors, you don't have to enforce this, but is infrared and collinear safety. So if you are computing these objects in perturbation theory, so or in a perturbative gauge theory, you have, in general, singularities as particles become soft or collinear. And so one way that you can test whether or not an observable is infrared and collinear safe is to measure the observable on some state, and then check if that observable is modified if there is either a soft emission or if there's a collinear splitting. And so what we can do is we can just test whether or not these detectors or an observable form for these detectors are infrared and collinear safe. And this will also motivate why there's more interest in some of these than others. So the first thing we can check this for is for this energy or ANEC detector. So let's say we just initially, so we've studied so far this free particle state, which is going into my detector, and it has some energy E. And so now what we want to do is to test that, and so this will just give out E from my detector, if I have the detector at a specific angle. And so now what I need to test is if this particle emits a soft particle, or if it splits into two, that I get back the same answer. And so first it should be, as you said, you are not worried about soft singularities because you explicitly have this energy weighting. So if I now have this particle which is going off, and it emits some very low energy particle, so this one will still have kind of E times 1 minus epsilon, and this will have some little epsilon energy like this. So now what can happen is my energy detector can land both on this particle or on this particle. But because it's explicitly weighted by the energy of the particle, this one will give an epsilonically small contribution, and so will just be suppressed in the limit that epsilon goes to 0. And so because of the explicit energy weighting, it kills it. Kills the soft contribution. So you get the same answer whether or not you emit a whole bunch of these soft particles. And so this one is, so it's soft or infrared safe. So now what you can worry about is if you have this particle, and so it splits into two. And in particular, what you need to consider is when those two particles are really exactly on top of each other along the same direction. And so now what you have is one particle with energy E, and then you have a particle here with E1, and a particle here with E2, where E1 plus E2 is E. And so the important thing about this energy operator is it's linear in the energy. And so in particular, what will now happen if you use this formula here, where it will sum up all the different particles coming in with a linear weight, that when they're exactly on top of each other, the detector will now pick up both this particle here and this particle here, and it will give E1 times some delta function plus E2, and so this is just the same as on the single particle state. Like this. And so because of the linearity in energy, it will just add back up to give the exact same result.
But what if you end up in two different pixels, right? If you're just like in the edge?
So this is the same as this, that you only need it to be true in the limit. And so here you can really think of it as like, this is an infinitely resolved pixel, and so it only needs to be true when it really splits at like 0 angle. And so this is why when we compute these later, as you go to this limit, it can have some, like it will have a divergent scaling behavior, but it will not diverge, like you will not get a non-zero answer for finite angle. So you'll get some behavior that it likes being more and more and more at small angles, but you won't just get infinity. And so in particular, the behavior in a conformal field theory will go like 1 over z to the 1 minus some particular anomalous dimension. And so it will definitely, like, it will like to be there because of this, but it won't give just like, you will not compute and get like an infinity. And so related to that, you can consider kind of two variants of these observables.
I have one more question.
Yeah.
You have the electron temperature, which is spin 2, and cumulative charge current operator, which is spin 1.
Yeah.
You can have in general high spin current in theory. Is there any limit on what's being is allowed?
There's nothing, so you may run into problems, but generically, no. You can write down these detectors, and then you have to understand whether or not they exist in your theory. And so that's kind of an open problem in general. But there's an interesting, like this is kind of related to this thing I mentioned about how do you constrain theories that do not have an S matrix. And so there's a nice paper by Malacina and Sasha Zhavodov on if you have exactly these higher spin objects, in a theory, you can use this kind of toy under some constraints. You can study whether or not that theory is consistent by using these correlator type observables. And so it's called like constraining higher spin theories. And so it's an interesting thing to do. I think there's no general answer to whether or not these are kind of well-defined or not. And so in that case, they're often kind of free theories, but you can try writing them down and understanding them, and is an interesting thing. It's just often in the real world, or these are heavily motivated by what you can do in the real world. As we'll see in a second, that even the charge one is not infrared safe. And so for real world applications, one is often interested in ANIC. But more generally, you can consider just any object that you put, or you can put into this object. Yeah.
Your presentation of IRC safety, is Sudakov safety a subset or a superset?
Good. So that is a very good question. And so I don't even know how to define Sudakov safety in a general theory. And so that's a very good, so there's kind of different spaces. So there's like, even within this, so there's like, let's say IRC safe observables. And then there's well-defined detectors. And so the well-defined detectors is definitely, and I'll show it in a second, and is definitely bigger than IRC safe observables. But the exact kind of boundaries of these two is not known. And so that's a good question. So we can chat more after, but I don't even know how to, if I don't have kind of particles, define an IR or a Sudakov safe observable. It's an interesting question, but I do not have an answer. Because the language for them, I don't know how to define it in a generic theory, but it's very, I mean, that's why part of the interest in exploring what are these well-defined detectors is kind of an interesting question. And so in the last few minutes, I just wanted to give two other examples of these types of detectors for testing these properties of IRC safety. So just to see if people are paying attention. So one thing one could define is some object which measures, so you can define a detector, which measures the energy of a particle to some nth power, where n is bigger than 1. And so does anyone understand, or can anyone guess whether or not this is IRC safe? Okay, and why not? It's not linear, yeah, good. And so then for the charge, if I measure, for example, electromagnetic charge, is this infrared or collinear safe? No, okay. And so the reason is I can have, for example, some quark going along, which radiates an infinitely soft quark like this and becomes a gluon. And so I can kind of bleed off charges. And so one thing, so this comes from, so this one is soft safe. So this is collinear unsafe. But soft safe. And so this one is soft unsafe. And so we'll see later on that this one actually leads to a well-defined detector because these collinear singularities will actually be associated with the detector itself. And so we'll be able to kind of renormalize the detector to give a well-defined observable. Whereas this one will not really lead to a well-defined detector in, for example, the real world. But we'll get to that later on. So this is where we'll start to see there's some distinction between these well-defined detectors and infrared and collinear safety. Okay. So I just want to conclude by or set up for the next time by saying why this is a useful thing to do. So we've now defined this nice observable here, or this nice kind of detector operator. And so now what can we do with it? So what this allows us to do, so the reason why this is nice is it allows us to define a set of observables which we can measure in collider physics. So for example, I can have I have my vacuum, I can act with some local operator on either side, and we'll define exactly, we can choose our operators next time. And now I can just stick in a bunch of these energy flow operators at different points. And so what this is like doing is exactly what one does, for example, in jet physics, that one wants to study kind of correlations in the energy flux, which comes off to infinity. So I can put some detector at one angle here. And some detector at another angle here. And so the nice thing about this particular object here is even if you're not a collider physicist, because this is just an integral of this local operator shown here, if your friend gives you, so this object can be obtained so if your friend happens to have a bunch of correlation functions of local operators of the stress tensor, like this, then this is some object that, as I said before, people study. So these are now at some different local positions. So this is now an object which people study, for example, in generic conformal field theories. And so if you're given this object, we'll now be able to apply or kind of use this detector operator transform to uplift this to actually answer interesting questions about collider physics. And so now what this motivates is trying to understand the structure of these correlation functions in different field theories. And so this is where the relation to conformal field theory comes in. So of course, this could be done in any field theory. But in a conformal field theory, it's very nice. You can often get nice results for the structure of these correlators, or they're very highly constrained. And so we'll be able to study the behavior of these observables or these correlation functions in a conformal field theory, and then kind of uplift them to actually understand the structure of interesting correlations in energy flux. And so what we'll do next time is we'll start kind of trying to build up towards these actually interesting questions. And we'll study first, so we'll kind of move from things that are fixed entirely towards actually interesting observables. So first, next time, we'll study just 2-point correlation functions and show how these are related to what in particle physics we would typically call total cross sections. Then we'll study the structure of a 3-point function, so with a single insertion of this. And so this can be viewed as in the state, kind of how energy is distributed on the sky. And so these are still a relatively simple object that are largely fixed by symmetries. And so we'll show kind of how these behave in different theories and how we can extract the kind of 1-point correlation function from that. And we'll do this in some supersymmetric theories where you can actually fix this object exactly. And this will lead to some nice constraints. For example, from this ANEC, And then we'll move towards the actual kind of goal of measuring something which contains interesting dynamical information and kind of scaling behavior, which the third, and so the third is the object will actually be of relevance for collider physics, where we have two of these energy flow operators. And so this is now, in the conformal field theory language, a 4-point function. And so generically, these are not known. And we'll show how these can be analyzed using a kind of operator product expansion for these objects, which predicts the kind of scaling behavior in different kinematic limits, which one can measure in collider physics. And we'll relate this to how we'll try to relate this operator product expansion to what is typically done in the study of effective field theories. And I'll try and precisely map out some of the relations to what Stefan will presumably talk about in his lectures. And this is where an actual observable, which has interesting consequences from colliders. So this is the kind of, it will build up very slowly from simple things towards hopefully getting somewhere interesting. But this will be what we'll do for next class. And so that's it for now.
Let's stop here. Time, since our next one is in an hour. So again, if you bring this, make sure you have your photo ID. If you don't have either of those on you right now, we'll get it. We'll be in this class area.